Hello, everybody. Let's have a quick chat about binary. What is it? How do you think about it? And then we could talk about the algorithm for converting from decimal to binary. And then we could talk about the multiple choice problem that was a recursive version of that algorithm. Okay, so decimal is the base 10 number system, which we use. And we'll talk about what that means in a second. And binary is a base 2 number system that electronics use, digital electronics use. So what is this base system about? Way back in elementary school, you learned that each position in a number means something different. So this is, when I was in elementary school, this was called the ones place, this was called the tens place, and this was called the hundreds place, because each of these numbers tells you how many ones, how many tens, and how many hundreds are there in this number. So the base system is a way of breaking down your number into a certain number of powers of 10. So here I have 7 ones, and here I have 3 tens, and here I have 2 hundreds. And maybe it would be better for me to use 2 colors here. So if you write 1 and 10 and 100 as powers of 10, this is 10 to the 0th power is 1, and this is 10 to the 1st power is 10, and this is 10 squared is 100. So that's the base system. And so we can take this idea, except instead of decomposing your number into different powers of 10, we can decompose your number to different powers of 2. So I guess let's start over here and then go backwards. So what if instead of saying I have 2 hundreds and 3 tens and 7 ones, what if I say I have 1 times 2 squared plus 0 times 2 to the 1st plus 1 times 2 to the 0. So notice the only thing I've changed here is I've changed the base from base 10 to base 2. So how do we interpret what this is about? Let's go backwards. So 2 to the 0 is 1. 2 to the 1 is 2. 2 squared is 4. So just like this was saying I have 2 hundreds and 3 tens, this is saying I have the number 101 in binary means I have 1 4, I have 0 2s, and I have 1 1. So going up one more step, just like in base 10, this was the ones place, hundreds place, tens place, hundreds place. This is like the ones place. This is like the 2's place, this is like the 4's place. So in binary, it's telling you how many 1s, how many 2's, how many 4's in your final number. So we could actually figure out in decimal what is this number by saying, okay, I have 1 times 4 is 4, plus 0, plus 1 times 1 is 1. So this should be the decimal number 5. But you can really just almost do it in your head if you think about it this way, because you can just say 1's place, 2's place, 4's place. If we had a larger number, this would be the 8's place, this would be the 16's place. And each digit is either a 0 or a 1, because it's binary. And you can just add in your mind and say, what decimal number would this be equivalent to? So I've got 1 1, 0 2's, and 1 4. 4 plus 1 is 5. If this was 1 and 1, then I'd have a 16 plus 8 plus 4 plus 1, which is 29. Okay, so that's the base system. Okay, so now let's talk about how we can convert from decimal to binary. So let's say we're going to convert 17 into binary. We know that we're going to have a number of binary digits, so maybe it's going to be like 100100 or 011101. So the first thing is figuring out how many binary digits are we going to have. A nice way of thinking about this is we know that the thing in the 30 seconds place can't be a 1, because that would imply that our number over here has at least one 32 plus some more stuff. So because our number is smaller than 32, I know that this digit must be 0. And it's just like in decimal, if you said like, what number is 0100? You'd be like, well, that's weird. that's like 100, but you wouldn't really ever write a leading 0 here. So that's what we're realizing here is to write 17 in binary, you wouldn't have this leading 0 digit. So you want to start with the first non-zero digit. Because 17 is larger than 16, I know I need at least one 16. But let's not start from this end. Let's actually label these as unknowns. So this is unknown digit 0, this is unknown digit 1, unknown digit 2, unknown digit 3, unknown digit 4. Now, I just want to acknowledge that in your mind you could probably decide what this was very quickly, but what we're trying to do is we're trying to come up with an algorithm, a step-by-step process that would let us determine what these are kind of no matter what it was, even if we couldn't do it easily in our own heads. Okay, so remembering how this number is formed, imagine that we're going to sum a bunch of these products vertically. So each of these x's is a variable that represents the digit. Could be a 0 or could be a 1. And for each of these, we're going to multiply that digit by its place value. So whatever number we wrote up here, if we wanted to know what it was in decimal, we would say, oh, we have 1 times 16 plus 0 times 8 plus 1 times 4 plus 0 times 2 plus 1 times 1. And then we would add all those up. So it's like we're adding these pairs. And my notation's a little bit weird here, but hopefully it makes sense. I'm imagining multiplying these vertical numbers and then taking each of those multiplied pairs and adding them together. Okay, so let's do some algebra. What I'm noticing about all of these things we're adding up is they're all even except the last one. Because here I've got 2, like 2 times anything is even, and 4 times anything is even, and even, and even. But 1 is either going to be even or odd, depending on whether this is 0 or 1. Because if this is 0, then 0 times 1 is even, because it's 0, and 0 is an even number. Or if this is 1, then I'd have 1 times 1 is odd. So because my number over here is odd, and I know this number on the right-hand side also needs to be odd, that tells me that x sub 0 has to be the digit 1. So now I have solved for my first digit. So I know the last digit's 1, and I've written the rest of these unknown digits in a more conventional format. So let's use that same trick to try and solve for the next one, thinking about evens and odds. If I subtract the 1 from both sides, I will get 16 on the left. And now all of these terms are even. So if I divide everything by 2, now I have 16 divided by 2 is 8. If I factor the 2's out and divide, I'll have this unknown digit times 8, this unknown digit times 4, this unknown digit times 2, this unknown digit times 1. And again, we can say, is the number on the left even or odd? It's even. All of these terms are automatically even. So if the term on the left is even, we know for a fact that this multiple of 1 has to be even also. And the only way for it to be even is for this digit to be 0. So now we've solved for the next digit. So this must be 0. We can solve for the next digit in the same way. All of these terms are even, as is this, so let's divide by 2. So now we've got 4, 2, 1, and unknown digit, unknown digit, unknown digit. And they're being added together and multiplied. And then same thing, even or odd. So even, therefore this digit must be 0 to keep this whole sum even. So far, let's write down what we've learned so far at the top. So we've learned this digit is 1, this digit 0, this digit 0. Let's keep going. Divide by 2. So I've got 2 equals 2 times 1, and then this is x4, x sub 3, and we are multiplying and adding. It's even on the left, therefore it has to be even on the right, therefore this digit has to be 0, because otherwise we'd have a 1 there, which would make it odd. So this digit is also 0. All right, last digit. So we'll divide by 2. We'll divide by 2. So that gives us the last digit has to be 1. And we can double check that this makes sense, and this is probably what you did at the very beginning in your own head. 1, 0, 0, 0, 1, so 1 is in the 16's place. So we have 116, no 8s, no 4s, no 2s, and 1, 1. So 16 and 1 makes 17. All right, so, what was the point here? Let's step back and try and look at the process that we used to determine these digits. What we did was we looked at our value that we were trying to make, and we asked if it was even or odd. And if it was odd, we learned that our smallest digit has to be 1. If it had been even, we would have known this digit has to be 0. And then what we did was we divided by 2. Actually, we subtracted by 1 and then divided by 2, but if you imagine integer dividing by 2, it would be the same either way. If this digit ended up being 1, we would subtract 1 to make 16 and divide by 2 to get 8. If this digit had been 0, then we just divide by 2 to get 8. But if you imagine integer dividing 17 by 2, you get 8 either way. So our steps so far are, let's write them down. So we've got, if our number here is odd, then our digit's 1, otherwise it's 0. Then the next step was integer divide by 2. And so now we're at this stage. And now we can repeat to find the next digit. We can ask, is this even or odd? And if it's odd, we know our next digit has to be 1, otherwise it's 0. And then we divide by 2 again. And we keep doing this until we run out of digits. So I'm intentionally making the pseudocode a little bit vague here because I want you to think through how would you actually implement this in real code. But I'm trying to walk you through how would you go from kind of an algebraic kind of logical derivation to noticing what steps you're taking as an algorithm. Let's express it as pseudocode, and then you'll do the last step. So for the rest of the block, why don't you do the classwork, which is try and write an algorithm, write a method that does this without recursion, and then look at the multiple choice question that was the recursive version of this, and then you can hopefully have more context for thinking about what is it doing. Good luck.